Hi everyone. My name is Irene Cobo. I'm a postdoc Juan de la Riva postdoctoral fellowship in the Institute of Forest Science in Madrid, Spain. And I am going to present the research line that I have envisioned as a part of my postdoc, which is entitled Joining Artificial Intelligence with Human Expertise in the Plant Big Data Era, a paradigm shift to improve forest health and productivity in a changing climate. So first of all, I'm going to highlight the importance of preserving forest health and productivity under a changing climate. So, well, as we all know, forests offer major nature-based solutions to climate change, biodiversity loss, land degradation, hunger and poverty. And also, in a post-COVID era, healthy, productive forests must be maintained in order to reduce the risk of future pandemics. And this is because when some species become extinct, those that survive are more likely to host potentially dangerous pathogens. Among all the biotic and abiotic stresses that are threatening forests, recurrent drought is one of the main climatic factors, especially in the Mediterranean region. And this is the reason why the knowledge of the molecular basis of the adaptation of trees to drought is key nowadays, because it allows the identification of molecular biomarkers that are related with this drought resistance, and they can be used to guide management strategies such as marker-assisted selection or breeding. However, this knowledge is scarce, especially in the case of conifers due to their huge and complex genomes. And I'm speaking about conifers as well because they have also great ecological and economic importance as sources of renewable and natural raw materials for bioproducts, bioenergy, and biofuels. So they can really contribute to the new bioeconomy proposed by the European Bioeconomy Strategy 2018. And among all of them, maritime pine or Pinus pinaster is one of the conifers with the greatest socioeconomic and ecological importance in South as a source of bioproducts, as I have mentioned before, such as wood, resins, but also, and most importantly, given its great adaptive capacity. So it makes it an excellent model to address these questions, and this is why this is going to be the model species of my research line. So as I have mentioned before, this understanding of the molecular basis of drought resilience will allow this identification of biomarkers that can be used to guide the design of conservation and management strategies. However, it is challenging from an analytical perspective because it requires the integration of disparate data types, genotypic, phenotypic, and even environmental information. And also, in addition to that, the recent advances in sequencing technologies are enabling the generation of large amounts of omics data. And this is coupled with both the high throughput phenotyping, the so-called phenomics, which allows the phenotyping of thousands or hundreds of individuals in a fast way, in an automatic way, in contrast with the manually phenotyping that has been done so far, which is very promising. And also the fine resolution environmental data, such as LiDAR and other related remote sensing approaches. So we can talk about the new era of big data in plant biology, which is very promising because we can ask and answer questions unprecedented so far. But on the other hand, it poses a challenge from this analytical perspective because we need to integrate huge, complex and also heterogeneous data sets. So in this sense, the machine learning, which is a branch of artificial intelligence, offers promising approaches to integrate these large and heterogeneous data sets in order to recognize, find patterns, and also relationships in these complex data. Although these artificial intelligence approaches are in their infancy, we can say, in plant biology, they have been already successfully applied in biology. For instance, the well-known AlphaFold application that can be used to identify or to predict the secondary structure of proteins with unprecedented accuracy. And in addition to everything, also integrating human knowledge into these machine learning algorithms, the so-called expert augmented machine learning, has been proved to deliver superior and optimal performance, for instance, in fields like biomedicine, and also it has been stated many times during this conference that machine learning is not magical. So including some of our expertise in the selection of the data sets that we are going to use for the machine learning predictions can enhance this machine learning algorithm performance. So considering all this background, I'm going to present the objectives of this research line. The first one is to leverage and to automate the identification of drought-resistant pinospinaster trees. And to do so, I'm going to integrate different data, multi-omic data, phenotypic data with human expertise to develop experimental machine learning algorithms that will allow us to identify biomarkers related with these drought resilience in pinospinaster trees. And to do so, I'm going to use multi-omic and phenotypic data that has been collected for more than 20 years by our team. This is the potential that I saw when I arrived to this team, was that the huge availability of metabolomic, transcriptomic data, epigenomic data that were analyzed independently. So I decided to integrate all this data, to analyze together all this data in order to make the most of the data, to get more information from the data. And machine learning seemed to me a good approach to do that. However, there is another limitation, and everybody working in conservation genomics maybe know that, which is the existing gap between molecular research and practice. So sometimes you end up with a bunch of candidate genes of drought resistance, for instance, but the question is, are these genes actually useful for implementing conservation strategies, for instance? So the next step, in order to help bridge this existing gap, I'm going to prioritize the biomarkers based on their measurability using these high-throughput phenotypic technologies. So again, I'm going to integrate the phenotypic and multi-omic data from our team, using machine learning algorithms, of course, but I'm going to integrate this human expertise in order to prioritize the biomarkers that are actually measurable using these high-throughput phenotypic technologies. So I can identify useful markers for these conservation strategies. And in order to ensure the applicability of these machine learning models or biomarkers to a wide diversity of case studies, we are going to collaborate with other research teams and enterprises that they are going to provide us data in order to test the machine learning models and refine them. And finally, in order to ultimately test the usefulness of our biomarkers in the design and implementation of forest management policies in Spain, we are going to collaborate with the Ministry of Ecological Transition and Demographic Challenge in order to learn what are the data or the useful data or biomarkers in order to implement these policies. So this is basically the workflow we are going to implement, we are implementing right now. So the first of all is the data pre-processing, because it is key to enhance the performance of the machine learning algorithms, like clean, format, and normalize the data. Then we are going to try to fill the gaps in our data sets, because, for instance, we don't have all the metabolic pathway memberships of all the genes and metabolites. So we are going to design a machine learning model in order to make these predictions, including it in the data set, in order to increase its prediction power. Then actually develop the machine learning algorithms to obtain models to identify these biomarkers, potentially conferring drought resistance. And of course, including this expert information in order to prioritize those biomarkers potentially measurable with these high-throughput genomic technologies. We are going to test finally the models in other pinospinaster materials, and finally we collaborate with policymakers, as I have mentioned. So we are currently in this step. We have been taking courses and training courses for learning, because this is a huge learning process, and we are now pre-processing the data, so this is why I'm not presenting any results. And just for future directions, our future objectives, apart from completing all these objectives of this research line, the first one is the creation of a machine learning working group, which I consider key to speed up the advancement of these this promising field, which is the application of artificial intelligence in forest management. So I think it only can be done by learning from each other. So this is one of the future directions I have in mind. And the second, of course, looking for collaborations, because again, this is a multidisciplinary field and we need to collaborate with each other in order to make the most of our data. So if you are interested in any of these activities, please don't hesitate to contact me, either in my email or my Twitter account. And well, last but not least, I would like to thank all my amazing team I'm working with, also the funding sources, of course. Without them, this project wouldn't be possible, and to you all for your attention.